In today's exercise, we are counting the number of ways that selections can be made. Now, the two things that you need to think about every time are, do we care about the order that we choose the items or not? Now, in the next three exercises, we're going to be considering selections where order does matter. And after that, we'll consider unordered selections. Now, if the order is important, you then need to think, can we replace or have repetition of the same item? So those traditional probability questions where you've got, say, a bag of lollies and you're wondering how many different ways the different colours can be pulled out, it makes a difference whether you're allowed to take each lolly and put it back or whether you actually eat it and now there's less lollies every time. And what you're going to see is that if repetition is allowed, in other words, we can put the lolly back and choose it again, then we get many more ways that we can make our selections because we're always putting things back, so we've got more things to choose from. Whereas when we're not allowed to replace items, we generally see factorials creeping into our calculations because every single time we make a selection, there's one less lolly in the bag, so to speak. And so we multiply by a smaller number each time, and we end up with factorials in a lot of those questions. The multiplication principle with selections is really quite simple. It's so important with counting, though, it's actually called the fundamental counting principle as well. Now, if we've got a multi-stage selection to make, and there's lots of stages, let's say there's R stages, then if we can make the first selection in a certain number of ways, let's say A ways, and we can make the second selection B ways, and the third selection in C ways. Now I've put ... here to show that we could keep on going making more and more selections. Then the number of ways that we can select R items, remember that's how many stages there are, is going to be A multiplied by B multiplied by C, and we could continue on multiplying by D, E, F, etc., depending on how many stages there are. Now the easiest way to understand this in action is to look at an example. A restaurant has 4 entrees, 3 mains and 5 desserts on their menu. How many ways can I order a 3-course meal where I'm getting one of each type of meal? Well, you can use these boxes just to show yourself the number of combinations of each. We can see that there's 4 entrees, 3 mains and 5 desserts. We need to multiply these. This is the multiplication principle for a reason, but it makes sense that no matter which of those 4 entrees we have, each one of those could go with 3 mains. So if you imagine this as a tree diagram, there's 4 entrees, but once you've got to each point there, you can take 3 different mains. And so it makes sense that there's 12 things that can happen at this point. But then if there's 5 desserts, we've got 5 branches coming off the end of each of those 12. So that explains why we're going to need to multiply the 12 by 5. Now the boxes are helpful if you want to write in what the choices are, and that can be useful in a complicated problem so you don't get mixed up. Other people won't bother with the box. They'll just put 4 times 3 times 5, or actually even reach for their calculator, put the numbers in if they're complicated ones, or just have a look at it and say, I can see that there's going to be 60 different ways that I can order dinner. Let's start by looking at how many ways you can make an ordered selection when you are allowed to repeat an item. So easiest way to do it is to probably start with an example. How many 3-letter words, now I've put the word words in inverted commas there because we don't need our words to be proper words in the English language, it's just a combination of letters. But how many different 3-letter combinations of letters can I make if I'm only allowed to use A, B, C, D and E, and repetition is allowed? That means I could have A if I like. Well, this method here is quite handy when you're learning. After a while, you'll probably just see what numbers need to be multiplied together. But the idea here is that you can use boxes to think through how many options there are for each of your letters. So when you go to select a letter to be in the first letter of the word, there's 5 different letters to choose from. Repetition is allowed, so there's still 5 letters to choose from for the second letter and 5 letters to choose from for the third letter. And we need to multiply all of these together because for each of these options, A, B, C, D or E in that first position, there's 5 options for the second position. And so it's like a massive tree diagram that's going to have 5 times 5 times 5 branches. Or we can write that as 5 cubed, which is 125. Now, when you're using this method with boxes, some sorts of questions will lend themselves to this situation where you've actually got the same number in each box and you've got an index expression. Other examples will use this multiplication principle with different types of items. And so the box method still works with both types of questions, as you'll see. So we can come up with a bit of a generalization here, or a rule. If repetition is allowed, and we're making words that are long or R letter words from N letters, then we can make N to the power of R of them. N to the power R words. Now, you can memorize this as a general principle, or every time you get a question like this, you can literally just think through, well, what are the options? I've got 5 choices times 5 choices times 5. Oh, I need 5 cubed. And that's probably the better way to go, because if you memorize something, you can easily mess it up and get it the wrong way round. So think freshly each time. Now let's look at an example that's almost identical, but there's one crucial difference. This time, repetition is not allowed. So if you imagine a little bag containing your 5 letters, when you've taken one out and used it as your first letter, and there's 5 different choices that you could make there, there's now only 4 letters in the bag. So there's only 4 different ways that you could choose your second letter, and there's only 3 different ways that you could choose your third letter. Now, it's easy to see here that what we have is 5 times 4 times 3. And so we can see that we've got 60 different ways to make this. But if we were to come up with some sort of formula for understanding how we can, I guess, make a shortcut for questions like this, we can see that factorials are sort of involved, because we're going down with one less choice each time. But we didn't go all the way down to 1, did we? We stopped somewhere. And as it turns out, what we actually did here is we did 5 times 4 times 3 times 2 times 1, but to get rid of that times 2 times 1, we need to divide it by 2 factorial. Effectively, this will give us the exact answer that we need, and it gives us something of a formula as well. Now, how did we get this 2 factorial for the bottom of our little recipe? Well, we saw that 5 factorial really looks like this, doesn't it? 5 times 4 times 3 times 2 times 1. And we wanted all of the first part, but we didn't want the tail of it. So if we put the tail down there, we can see that they will cancel, and we'll just be left with the part that we want. Now, the size of the tail is always a factorial that's 1 smaller than the last thing that we had. So how can you equate here? What's the relationship between 3 and 2 and 5? Well, 3 plus 2 is 5. So we've got a little formula here that we'll use all the time from now on. And this one is a good one to remember and to know. We can make this many R letter words from N letters if repetition is not allowed. Now we've got N factorial on the top, and on the bottom we've got N minus R factorial. And in this example, we would say we'd need 5 factorial on the top, and on the bottom we need 5 minus 3 factorial, which is of course 2 factorial. And that method of unrolling helps us to work these sorts of questions out quite quickly and easily. Now, this notation here has a special name that we'll look at. It's called a permutation, and we can also write it like this. And we'll have a look at that in a bit more detail now. Now, the tricky part is that most questions that you'll see in this course won't actually state whether or not there's repetition. So you need to think for yourself whether repetition is appropriate or not. So here's 2 examples where we need to just think for ourselves and apply what we've learned. How many 4-digit numbers can I make using only odd digits? All right, well, if I'm only using odd digits, then I've got to think, how many are there? There's 1, 3, 5, 7, and 9. So there's 5 different digits that I could use. Now, if you're a formula memorizing type of person, you might be jumping straight into going, oh, it's 4 to the power of 5. Oh, is it 5 to the power of 4? And that's where your problem might come in. Perhaps you'll be fine with it, and if you can get it around the right way and that's your method, go for it. I prefer to just think through, well, how many things could the first digit possibly be? It could be 5 different things. And what about the second digit? Can I repeat digits in numbers? Yes, that seems fair enough. So obviously I can repeat. So there's going to be another 5 and another 5 and another 5. Now already I'm thinking about writing out this, but in my head the fact that I've formed that means that I can sort of take the shortcut, save myself a little bit of time, and actually cut straight to that. And then I can reach for my calculator and go, well, I've obviously got 5 to the power of 4, which is 625, and I can make sure of it with my calculator and put it in. Next question, how many ways can I choose a president and a vice president from the 20 people in our class? Well, would it be reasonable for one person to be the president and the vice president? Probably not. So even though it's not actually stated in the question, I can use a little bit of logical thinking here to realise that I'll probably think of how many ways I can make the president, and that would be 20 because everybody in the class would be eligible. But once I've chosen that president, there's only 19 people left, aren't there? And all of those have a chance to be the vice president. So now I need to multiply these numbers together and I'll get 380 different ways that I could make that choice. Now, if we were to use that permutations formula that we've just seen, which we'll look at it in a bit more detail, we would see that we've got 20 factorial over 20 minus 2. And that's because we're choosing two things, factorial. And that basically gives us 20 factorial over 18 factorial. And if we unroll the top, we've got 20 times 19 times 18 factorial. The 18 factorials cancel, and I've just got 20 times 19. Now, I think you can appreciate how using the formula is great, okay? And for many people, it's the way that they'll want to do it. But sometimes just thinking, well, how many ways can I choose the president? 20. How many ways can I choose the vice president? Oh, well, the president's gone. I've got 19. Sometimes this gets you to the answer much more quickly and easily.